Let's take a first look at one of the most important equations in all of mathematics, known as Bessel's ordinary differential equation. Bessel was an astronomer, and this equation came up in his studies. So, as written, you'll notice that the differential equation has a singular point at x equals 0. For your reference, the singular point of a differential equation is where the coefficient of the highest order term is equal to 0. So x equals 0 is a singular point, which means our study of this differential equation should involve singular series and not the regular series method. So we're going to use the Frobenius method, which I outlined in a previous video, and write the solution as follows. Y equals the x to the power something known as sigma, the characteristic exponent it's sometimes called, k equal to 0 to infinity, ak x to the k, with the stipulation that a naught not be equal to 0, because the purpose of doing this modification is to make sure that the lowest coefficient term is not a constant. So now that you have this, we can pull it inside and write it as k equal to 0 infinity ak x to the k plus sigma. The first derivative and the second derivative of the ansatz you have there would be k plus sigma ak x to the k plus sigma, and for the second derivative it would be y double prime equals 0 to infinity k plus sigma minus 1 ak x to the k plus sigma minus 2. Now if you put this all back into the Bessel's ordinary differential equation, you're going to get a long, complicated expression. It may be even worth writing it. So if I multiply this by x squared, the 2 factor disappears, and I'm going to get, so the ODE becomes the sum from k equal to 0 to infinity k plus sigma times k plus sigma minus 1 ak. I'll keep the factor of x to the k plus sigma outside, and then when I multiply, I made a mistake here, that's k plus sigma minus 1 here on this one. When I multiply this by x, that gets rid of the minus 1 there, so I get plus k plus sigma ak, and then lastly I have these two terms. Now x squared advances the degree by 2, so I'm going to write that as a separate, the next two terms are separate. And then I have sum k equal to 0 to infinity x squared minus nu squared ak x to the k plus sigma. So this equal to 0. This is the Bessel's differential equation, and now we have to make sure that the coefficients all respect this, which means that for any power of x, the right hand side must be 0. So it's convenient in a situation like this to make a table, which I'm going to do next. On this table, I'll write the power of x that I'm looking at on the left column, and on the right column I look at the coefficients. It's just a 2-column table. And here the purpose would be to set the coefficients equal to 0. So let's first take the power x to the sigma. X to the sigma is got in the first term by setting k equal to 0. So I'm going to get sigma times sigma minus 1 plus sigma ak. Now here the lowest term for the x squared multiplying it would be x to the k plus sigma plus 2, because x squared would go and add to the exponent. So you don't get any contribution from here. From nu squared you just get contribution negative nu squared ak. And all this must be equal to 0. Now notice that sigma squared minus sigma plus sigma is just sigma squared. So this gives me sigma squared minus nu squared a naught equal to 0. But as part of the ansatz of Frobenius, we have stipulated that a naught not be equal to 0. That's an important requirement. That leaves us with the condition that sigma must be equal to plus or minus nu. That gives us the two orders of the solution, which are going to be our two Bessel's functions. Let's try x to the sigma plus 1. This time you're going to involve k equals 1 from here. From the x squared term, there's still going to be no involvement because the lowest term is k plus sigma plus 2, and here you have k plus sigma plus 1. From the nu squared term, you have k plus sigma plus 1, so you get involvement there. By the same reasoning, I'm going to get sigma plus 1 squared minus nu squared a1 equal to 0. Now here, if sigma is equal to plus or minus nu, this term cannot be 0, because this is going to be plus or minus nu plus 1 whole squared, and that's going to be different than nu squared. So our conclusion is a1 equal to 0. And later on we'll see this implies all the odd coefficients will be 0. For now we'll just take that on faith, but I'll show you soon how that happens. What about the next coefficient, sigma plus 2? You're going to get the same pattern here, but with a2. But now what's going to happen is the first term from an x squared is going to kick in, because the first term you get is k plus sigma plus 2. So I also get an a naught from that. So this tells me that a2 is related to a naught. As a matter of fact, all subsequent coefficients of powers bigger than sigma plus 2 or equal to sigma plus 2 will have the feature that sigma plus k squared minus nu squared ak plus ak minus 2 equal to 0. This gives us a recursion relation, and that recursion relation is ak equal to negative ak minus 2 divided by sigma squared plus k sigma plus k squared minus nu squared, which I'm going to write as sigma plus k plus nu times sigma plus k minus nu. Now from this you can immediately see that if a1 is equal to 0, then a3 is equal to 0, a5 equal to 0, and so on. So we can immediately conclude that a3 equals a5 equals, and in general a2m plus 1 equal to 0, which justifies my comment made over here. The other thing you'll notice that is for even integers, this gives me a2m equals negative a2m minus 2, because any even integer can be written as 2m, divided by sigma plus 2m plus nu times sigma plus 2m minus nu. And that's really it. We have solved the problem completely. Now the only thing is, this is not how the literature reports this solution. They give it in a slightly different fashion. If you apply this procedure inductively for starting from a naught, you'll end up getting the following, and this is an easy exercise which I invite you to try doing. you're just going to get a naught divided by, so each time you're going to keep building up these denominator powers. So you're going to get 2 to the power 2m times m factorial nu plus 1 times nu plus 2 all the way to nu plus m. If this seems far-fetched, let's try a little to see that this works out. Let's do a2m. Well, that's from the we have to take sigma equal to something. Let's take sigma equals nu. If sigma equals nu, then I'm going to get a2m equals negative a2m minus 2 divided by, now if sigma equals nu, I'm going to get 2m plus 2 nu. That's where the factor of 2 comes from. So I get 2m plus 2 nu, and if sigma equals nu, then sigma and nu cancel out to give me just 2m. So that's another factor of 2. So you're going to get negative a to the 2m minus 2 squared m times m plus nu. Now if you keep doing this over and over, then you're going to start getting 2 to the power 2m. M factorial will show up because you keep descending in powers, and each time you go down you're going to get m plus nu, then you're going to get nu plus m minus 1, nu plus m minus 2, and all the way up to nu plus 2, nu plus 1. So you can easily show that this leads to that. Now once you have this, this is still not how it's usually written in the literature. Gamma functions are used, and for this what we do is we use a normalization that a naught be equal to 1 over 2 to the power nu gamma to the power gamma of nu plus 1. Gamma of nu plus 1 for integer nu is just nu factorial, but since gamma is a factorial function, even for non-integer nu, it's a well-defined factorial. So what this does is it functions as a zipper. As you close the zipper, one of the links keep linking to the next. So gamma of nu plus 1 starts a zipper rolling, because nu plus 1 times gamma of nu plus 1 is equal to gamma of nu plus 2. So if I have this denominator, it starts the zipper, gamma of nu plus 2, and then gamma of nu plus 2 times nu plus 2 is gamma of nu plus 3, and so the whole thing gets zipped up. And that's the way in which literature likes to write this. So given that, I get a2m, after zipping everything up, it's negative 1 to the power m. That same negative 1 to the power m, and this time I don't have a naught anymore because I've already chosen my a naught with that normalization, and that gives me 2 to the power 2m plus nu, because of this 2 to the power nu there, gamma m plus 1, which by the way is m factorial. I'm writing that also as gamma for symmetry, and gamma of nu plus m plus 1. And then you have this, that's it. That's the coefficient for nu. So the first solution, y1 equals j nu x, and it's going to be the sum of all these coefficients. times x to the k plus sigma. So that's going to be x to the 2m plus nu. X to the 2m plus nu and 2 to the 2m plus nu. So we can write this as x over 2 to the power 2m plus nu. And the other solution is minus So all I have to do is change this to minus, and I'm done. If nu is not an integer, then j plus nu and j minus nu are linearly independent, which means that we have solved the problem. What if nu is an integer? You can show if nu is an integer, then that's an easy exercise I'll leave for you to show, that j minus n equals minus 1 to the power n jn. In other words, they are linearly related, and so you can no longer have the second solution be given by j minus nu, or j minus n if you like. What to do then? Well, there is a second independent solution known as the Neumann solution, or the Weber solution, and I've seen it mostly commonly written as y, but sometimes also as n. So n nu of x, which is equal to sometimes y nu of x, and that's given by cosine pi nu j nu x minus j minus nu x divided by sine pi nu. So this is defined for all nu, and in general it's not a bad thing to always think of this as a second solution rather than j minus nu. It's another easy exercise to show that if nu is in fact not an integer, then writing it as linear combination of j plus nu and j minus nu is the same as writing it as a linear combination of j plus nu and j nu and y nu. Also, if you want to find things like nu equal to 0, observe that for nu equal to 0, that's a special case because plus nu and minus nu make no sense. So you're only going to get one solution, j naught, and the other solution has to come from here. However, if you put j naught here, that will not be a good thing. What you need to do instead is to take a limit as nu goes to 0 of y nu of x to get this function y naught. It's a pretty complicated limit, and the answer can be found in most reference books.